All right, so we're going to distribute binomials. And let me give you a heads up. This video is going to have a lot of talk, a lot of little calculations, a lot of writing. It's going to be hard to listen to. I already know that. But please bear with me and pay attention as well as you can, because in the end, the punchline is future math so much easier if you get this process under your belt. So let's go for it. So let's do it. We're going to distribute binomials, which basically means raise binomials to a power. So if I take a general binomial, a plus b, to represent all binomials, and I raise it to its simplest value, well, that would be a 0, and a plus b, anything to the 0 power equals 1. Okay, that was super easy. The next one also super easy, a plus b to the first power, well, that's a plus b. And let's write the coefficients, even though they're trivial, because the pattern will show up. It'll be a pattern that we'll use later. So squaring it, a plus b squared, well, we have a pattern for this, luckily. That's 1 times a squared plus a times b times 2. So that's 2ab plus 1 times b squared. All right, a plus b cubed also has a pattern, and that is 1 times a cubed plus 3 times a squared b plus 3 times ab squared plus 1 times b cubed. Now, you knew the pattern for a plus b squared. You may or may not have known the pattern for a plus b cubed. I'm relatively sure you don't know the pattern for a plus b to the 4th power, but I'm going to use it. So this is 1 times a to the 4th power plus 4 times a cubed b plus 6 times a squared b squared plus 4 times ab cubed plus 1 times b cubed. So you may now be asking, what is this magical pattern? In fact, there are 2 patterns working simultaneously. So let's look at the first one. First one has to do with the coefficients. Notice that for the first distribution, the coefficient was 1. I only had 1 coefficient. For the second distribution, I had 2 terms, each with a coefficient of 1. For the pattern we all recognize, the coefficient is 1, 2, 1, or the coefficients in order would be 1, 2, 1. And notice they're the same whether you go forward or backward. That's true at every level. So for the cubed binomial, 1, 3, 3, 1 is the same forward as it is backward. And finally, for the 4th degree, or to a binomial raised to the 4th power, I get 1, 4, 6, 4, 1. So that's the first pattern. And luckily, there's an easy way to find from one row to the next. There's an easy way to predict the coefficients for the next row. So for example, if I want to know a plus b to the 5th power, what would the coefficients be? And for that, we're going to use something called Pascal's triangle. And it looks like this. 1, which would be this one. 1, 1, which would be these 2 ones. 1, 2, 1, and then 1, 3, 3, 1, and 1, 4, 6, 4, 1. Notice that each step, all I'm doing is adding. I'm writing the numbers in diagonal, and I'm adding the 2 numbers diagonally before it together. So 1 plus 1 is 2. And over here, I'm not writing zeros, but 0 plus 1 would be 1, and 1 plus 0 would be 1. Over here, 0 plus 1, and so on. So on the edges, all I'm getting is 1s because I'm adding zeros to them. But 1 plus 2 is 3, and 2 plus 1 is 3. And all the way through the pattern, that's how the numbers are put together. So the first thing I can do very easily is I can identify the coefficients for the binomial expansion raised to the 5th power. So I know 1, 5, 10, 10, 5, 1. There's that palindrome I'm looking for. And so I know the coefficients for the a plus b to the 5th power already. Now a little note, I find it convenient if I can identify each row as belonging to a certain power on the binomial. And I do that by just writing a little sort of looks like a power. So to the 0 power to the 1st power, the squared, the cubed binomial, the 4th, the binomial to the 4th, and then binomial to the 5th. So that is just a little notation that I like to use to indicate which row I'm in. So if I wanted to distribute the same binomial to the 6th power, I would use 1, 6, 15, 20, 15, 6, and 1. And so at this stage, I can just keep going to find all of the binomial distributions I want, even though they are going to get more complicated as I go. They're definitely less complicated than, for example, if I wanted to find a plus b to the 4th without using Pascal's triangle. Well, let's look at that. A plus b to the 4th is the same as a plus b squared, quantity squared, times a plus b squared. But that would be taking this version, a squared plus 2ab plus b squared, and multiplying that by distribution to a squared plus 2ab plus b squared. All those distributions, combining like terms, praying every step of the way that I don't make a simple calculation error. And what would happen if I have negatives? Good Lord help me. So this is a really complicated process, and this is only to find a 4th degree binomial, or a binomial raised to the 4th power. So Pascal's triangle has some calculations involved, but it's certainly not the same mistake-laden process as simple distributions. All right, back to the process. So now that I know the coefficients that are going to go with distributing the 5th row, I have to figure out the variable configurations. And look at the pattern here. I'm going to jump in here at the squared. So notice that if I'm squaring the binomial, then a is squared, the first term is squared at the beginning, and the last term is squared at the end. So that's consistent all the way through. When the binomial is cubed, the first term is cubed and the last term is cubed. And when binomial is to the 4th power, the first term is to the 4th power, and the last term is to the, well, I made a mistake there. I bet you caught that. This would be a 4, and so for the pattern, this fits a 4. All right. Then inside of the expansion, there's another pattern. If a is cubed in the first term, then notice a is reduced by 1 degree in the second term, by another degree, and then finally in the last term, it's a to the 0 power, which we don't write down because that just equals 1. Same thing in working in reverse. The second term is the last term in the expansion with the same degree as the binomial, but descending backward. So 3, go backward 2, go backward to 1, go backward to 0, and we don't write it down. So the first variable descends in degree, and the second variable ascends if you're looking at it from left to right. So let's look at the expansion a plus b to the 4th. The first variable goes from 4 to 3 to 2 to 1 to 0, and the second variable goes from 0 to 1 to 2 to 3 until finally 4. So we have enough information now to put together the expansion of the 5th row. So the 5th power expansion of a plus b, starting with a coefficient of 1, a to the 5th power. Then moving on to the coefficient of 5, plus 5 times a to the 4th power. And now my b is going to jump on as a first power. B was 0 power here, plus 1 first power. Plus, after 5 is 10. A descends by 1. B increases by 1. Plus, let's see, 1, 5, 10. I need another 10. A decreases by 1. B increases by 1. Next is a 5. A decreases by 1. I'm not going to write the 1. And B increases by 1. Plus the last coefficient is 1. A is now to the 0 power, so I'm not going to write it. B to the 5th power. So let's do an example, and I think I'll do a smaller degree or a smaller power, so it's easier to see what we're working with. Let's expand the binomial 2x minus 7, and let's expand that to the 3rd power. So I want to keep track of, I'm using this row, 1, 3, 3, 1. So let's keep track of both our coefficients and what happens to the powers on each term in our coefficient. So first coefficient is 1, first term 2x, and that has to be raised to the 3rd power. Then the next term is going to have a coefficient of 3. 2x, this time is going to be raised to the 2nd power, but now I'm going to bring in the negative 7. Which is just to the 1st power, because negative 7 to the 0 power would have been part of the first term. Plus, my next coefficient is a 3 times 2x reduced again just to the 1st power. And then negative 7 increases from 1st to 2nd power. Then finally, coefficient of 1, 3rd term, or 2nd term, negative 7 raised to the 3rd power. So now all I have is some simple calculations to work with. Let's start at the beginning. 2 cubed is 8, x cubed. And then I have a negative here, so I know I'm going to have a negative here because negative 7 to the 1st power is going to be negative times a positive. I've got a negative. 7 times 3 is 21 times 2 is 42. X squared, and then 3, I'm going to get the same value, the 42, well, no, I'm not, let me take that back. 7 squared is 49, negative 7 squared is 49, and then 3 times 2 is 6, I'm going to have to do this calculation on scratch paper, so 9 times 6 is 54, 6 times 4 is 24, and 5 is 29. So unless I've made a mistake, which is possible, I have 294x, and then negative 7 cubed, well, the negative is still going to be a negative, and 49 times 7, 9 times 7 is 63, carry the 6, 7 times 4 is 28, plus 6 is 34. So 343. I will admit that in the process of talking, writing, thinking, calculating, all of that, I may have made a mistake on these two coefficient values. You'll have to check my work and you can just let me know. Of course, if my values were critical, I would certainly recalculate or use a calculator to double check, but they're not so critical right now. So let's do one other thing, another example. Even though this has a lot of calculation time in it, it's definitely less calculation time than this kind of a distribution. So I was finding, this is the calculations it took to find 2x minus 7 cubed. Imagine if I wanted 2x minus 7 to the 4th power. I would have to do this process with these values. It would just get big and ugly really fast. You can see it already sort of got big and ugly here. So the whole value of using Pascal's triangle for binomial distribution is to get more simply, more methodically to the value you're looking for without huge mistake-laden processes. Having said that, most of the time with these giant binomials, what we really want is one term. For example, if I expanded 2x minus 7 cubed, I might have only been interested in the value of the 3rd term. And so calculating the 1st, 2nd, and 4th terms might have been just effort that didn't need to be done. And Pascal's triangle gives us a really perfect method for doing that. Suppose I want to find let's say the fifth term of the expansion negative 4x minus plus, you can tell I'm making it up, can't you? 2y. And we want to raise that to the seventh power. So I'm going to look for the seventh row or the seventh distribution of this binomial, but I'm only interested in the fifth term. So I want to pull down the numbers for the next row where I can work with them. So looking at the sixth row of, or the sixth power row of Pascal's triangle, let's write the seventh power row. So 1 would be the first coefficient. 1 plus 6 is 7. 6 plus 15 is 21. Notice how I'm writing a whole bunch of these. I'm writing them all out, but I don't really need those. Now that I know that I'm only looking for the fifth term, I could just go, well, I want here's the first, the second, the third, the fourth, the fifth term, which is going to be 35. But I'm going to go ahead and write it out longhand because I think when it's new to you, it can seem magical, and I want to show you that it's really pretty methodical. So 1, 7, 21, 15 plus 20 is 35. And now I can work backward. 20 plus 15 is 35, 21, 7, and 1. All right, so these are the coefficients for the terms of this binomial expansion. So let's find the coefficient for the fifth term. The fifth term is 1, 2, 3, 4, 5. That's going to be 35, as I predicted before. And then I have to figure out the first term, second term of the binomial powers. That means if the first term is A and the second term of my binomial is B, what are the AB powers like I used up here? Well, I can descend. I'm going to have a power of A and I'm going to have a power of B, and let's descend. This would have been A to the 7th, 6th, 5th, 4th, A cubed, and B to the, I could work from either end. I could do B to the 0, 1, 2, 3, 4th power, or I could say B to the 7, 6, 5, 4th power, whichever way I want to work. Now, having done that, that's just 35 times negative 4x cubed times 2y to the 4th power. Okay, I'm not actually going to do this calculation. I don't think you need to watch me find negative 4 to the 3rd power. Well, maybe I will do it. Let's go as far as I can without having to pull out a calculator. So negative 4 cubed means it's still going to be negative, and 4 to the 3rd power is 64. And this will have x cubed. And then 2 to the 4th power, 2, 4, 8, 16. Y to the 4th. So that equals 35 negative, I'm going to take that negative out, 35 times 64 times 16. That would be something I would have to find on a calculator or multiply out longhand. And then my variable configuration will be x cubed y to the 4th. So again, not necessarily easy, but certainly way better than distributing this number by itself 7 times and then finding the 5th term in the row. That would be insane. But Pascal's triangle for binomial distribution, not insane.